Thanks for the opportunity to present this little project of us, the evaluation of speaker diarization systems. So I was, as you see there, developing an app for testing and documentation of these speaker diarization systems that we use at the Bayerischer Rundfunk. Nowadays, everybody is, of course, talking about generative AI, but we think we have to also focus on the evaluation side. So that's why the focus of this project on evaluation. To get the terms clear, the term speaker diarization, I just thought we could dive into this. I could give a short insight what it is that I'm talking about, speaker diarization. It means partitioning an audio stream into homogeneous temporal segments based on the identity of speakers. So you see on the right side there is a screenshot of our media data hub at the ARD. So the Bayerischer Rundfunk is part of ARD, so we're using this to search for audio content, and also this is the place where you can see the output of the speaker diarization systems. You see there is a transcription shown on the right, and this has been done with automatic speech recognition, of course, but afterwards there was this step of the speaker diarization that made segments of segmented it based on different speakers. And this, why do we use this? It helps our journalists to skim through the audio content. It helps them to, it's like pre-structuring, so we can find it much more faster. And that's what we use, the speaker diarization systems at the Bayerischer Rundfunk and at the ARD. And yeah, basically they tell us who speaks when in an audio stream. And to understand the scope of this venture, to evaluate the speaker diarization systems on a bigger scale, like automatically, I just wanted to give you some numbers. We all love numbers and looking at them. So only in August 2024, the ARD had a total of about 28,200 hours of audio that had been processed with automatic speech recognition, and in second step, processed with speaker diarization. And the Bayerischer Rundfunk also sent these mining orders for transcription and speaker diarization with an estimated duration of 788 hours. So in short, this is a lot of audio. Only in 1 month, it's like 3.3 years of audio that goes through automatic speech recognition software and is processed with speaker diarization systems. And the problem is, we were just, like, we are having these vast amounts mined by our systems, but we are just like looking at the results and saying, well, it looks good. Doesn't look good, quality is good, it's not. So we needed some way to automate this process of evaluation. And so I started the problem analysis, and I asked myself the question, are we even evaluating? Can we call this evaluation? We have these, at the Bayerischer Rundfunk, we have two options for speaker diarization systems to include them. One from the ARD mining platform and one from a provider called DeepVA. And we were like, the testing process of this output was just non-automated. It was non-automated testing with more or less random sample files. And also we had no fixed data structures and databases for documenting these tests for this kind of evaluation that we did before. And last but maybe the most important point is we had no quantitative scoring system. And yeah, that was maybe the biggest problem. So we set some goals and objectives We wanted to become the guardians of the quality. It's a bit corny, but I like the pun, I read it somewhere. And in order to become the guardians of the quality, we wanted to be able to do three things. First of all, we wanted to be able to evaluate how good or bad is the output quality of the speaker diarization systems in general. And also we wanted to be able to compare different versions of a speaker diarization system. And not only versions, because I told you we have like 2 options for speaker diarization, so we also wanted to be able to compare these 2 speaker diarization systems. Yeah, and that's why in my final project of the traineeship that I did at the Bayerischer Rundfunk, I suggested building an evaluation pipeline, so an automatic pipeline that will compare the system output of these speaker diarization systems to a ground truth of perfectly annotated reference files, and this all in this automated pipeline. That's, yeah, and this pipeline is really no big magic. It's like some scripts that do these things. They post a mining order to one of the systems, and it gets back the mining result, and then we have to convert the mining result into a file format, because now the next step of the pipeline will be the most important. There is an open source toolkit called PyNote Metrics, and with this open source toolkit, we can like compute metrics from the results that we got from the speaker diarization systems. And in the end, the program will print out a test report or save it in a spreadsheet. Yes, so this is like the pipeline, and I want to go further into the metrics part, because this is the most interesting about the evaluation. And in order to do so, I will take a step back to speaker diarization in general. So what does speaker diarization do? We see here, this is an image of an audio stream, and the final result of a speaker diarization pipeline is this. We have a segmentation based on speakers, speaker segmentation. And so we can see the speaker diarization system has annotated the audio stream, and it tells us that Laura is speaking in the blue segments, and Leland in the red, and Maddie in the green segments. And it even detects where there's no speech. So there's also no speech segments. But to evaluate this speaker diarization system, we cannot evaluate at the last point of this speaker diarization pipeline. We have to start at the beginning. Speaker diarization system starts with the voice activity detection. So that tells us where there's speech and where there's no speech. So that's the first step of the speaker diarization pipeline. Afterwards, it will set some boundaries at the speaker change detection. Speaker diarization system sets a border where one speaker ends and another begins, or maybe a non-speech segment will begin. That's like step number 2. And step number 3, the speech turn clustering, the audio stream, the segmentation that we got from the step before will be assigned speakers. So now the system in this step can tell us where same speakers are speaking, like speaker number 1 is speaking in the blue parts, and so on, you understand. And as you see, we don't have the names of persons, we don't have the metadata from the persons yet, and this is what happens in the last step, the supervised speaker recognition. And it's a whole, I think it's a whole different world, the supervised speaker recognition and everything that happens before this, the diarization part. Yeah, but I showed you all of this not to educate on speaker diarization, but to make you understand where these scores and metrics now come into play. So each of these steps of the speaker diarization pipeline or module has its own metrics or the open source toolkit brings its own metrics. Like for voice activity detection, we have the detection error rate. And with this, we can basically evaluate how well the system recognizes if someone is speaking or not. And this all goes way down to the supervised speaker recognition, where we have a metric that is called identification error rate, and this tells us how well the system identifies speakers. You can, with these metrics, you can really go into details of evaluation, but maybe this is more for people fine-tuning these models, but also if you're really interested in where are the errors of my speaker diarization system, you can like be very detailed and use these detailed metrics. Most of the time for us, the third step, the speech turn clustering, is what we evaluate when we want to know is our speaker diarization system good or is it bad. So let's get back to the pipeline. So you see these metrics in step number 4, they come into play there from the PyNote metrics toolkit. And now to evaluate the output of a speaker diarization system, I wrote that there you need a ground truth of perfectly annotated reference files. And that is, you need a data set. You need a data set to compare your output against. And building a data set has always been kind of a problem for us. We want to have a data set that is representative of our archival content and not use some data sets that are out there that can be used. So we had to like perfectly annotate audio files before we could evaluate, and that's why we started small, just 3 audio files, just for getting into the this building of the data set, and then we could add some new to a bigger data set that's called data set large at this point, and that this has already about an hour of perfectly annotated audio to compare against. And we just recently found a way to build these data sets much quicker than we did before. I like to show you this. This is a software. It is intertwined with PyNote and PyNote metrics. It's called GryoNote, and it is a semi-automatic speaker labeling software or toolkit. And with this, it works like this. This is basically a speaker diarization system. It uses the speaker diarization of PyNote to annotate the audio stream. And if you find, as a user, any problems or any incorrect speakers, you can just go quickly over it and like correct the mistakes. And in the end, you have an RTTM file that you can use with the toolkit, and you have your perfectly annotated reference file. So this is like crucial for building larger test data sets, and we are onto this now to make it more representative. Part of this like proof of concept work that I did was a prototype. I think it helps to demonstrate how this all like kind of application this could be if you made it into, if you build a graphical user interface. Then you would have a simple structure with 2 main flows. The one main flow is the testing flow, and the other is the reports flow. With this, you would be able to test your speaker diarization system, to display the test results, and to save and export the test reports in the end. Works like the usual checkout flow, you know, when you are ordering something on the internet, you choose your speaker diarization system. We have 2, not everybody is using 2, but sometimes you are in the position that you have to decide on some. So you have to add some speaker diarization systems to connect them to this. So you choose your audio mining tool or speaker diarization system. You choose the data set, and in the end you choose which kind of metric you want to use. And as I told you, at the moment we are mostly just using the diarization error rate for it because it's a combination of the first two metrics. And then, yeah, nice, the test started successfully. I get a job ID and I can search for the job ID in this test report database. Sort and filter it and export and display the test results. Apart from this prototyping stuff, I think what's even more interesting is see this all in use. So I said it was a proof of concept, but we are already using the script version of this idea in our work. So I want to present you this use case that's called testing and update. And I want to explain the situation that we were in. I told you there is this IFTA mining platform where we have the speaker diarization service on it, and we have a model. And we know this model does a lot of mistakes. So the product owners of the mining platform, the developers came up with a new diarization model. And they put this new diarization model on the staging environment. And so we could test it. So in the end, we wanted to be, as I said, guardians of the quality. We want to make sure that this new version is better than the old one. Maybe we are a bit mistrusting in this case. And to spice things up, we just added an open source diarization model to the test to just see how it performs in comparison. So we used this data set of 17 files, still very small data set, and you have to be careful with numbers when you have such a small data set. And we started the testing in May and tested the speech turn clustering. So sometimes it's also called diarization, what makes it very confusing. So we tested this diarization models, the old one and the new one that was announced but not yet there. And we got some really interesting numbers out of our tests. So we wanted to know, how well does this speaker diarization system recognize speech and which segments of speech belong to the same speaker, the diarization task. And that's what we got out of it. So our old speaker diarization model on the RRD production environment, it had a really high error rate, a really high diarization error rate, of 20.4%. And to our great pleasure, the new diarization model that was announced had only a error rate of 3%. And that is a great development. And we were very relieved to see these numbers. And very interesting indeed, the Hugging Face open source software, it performed very well without any modification, without any fine tuning. We had a real nice number there of only 4.4% diarization error rate. And yeah, of course perfect would have been 0, but yeah, who gets this kind of numbers? Nobody does. Yeah, so this empowered us to report to our supervisors, yes, we want the new model, tell them to implement it, tell them it's going to be great. And so we told them the new the diarization model shows a 7 times smaller diarization error rate, which is great. And the interesting side note is the Hugging Face, as I said before, the Hugging Face open source diarization model showed an error rate that it was already 4.5 times smaller than the former the diarization without any modifications. So our experts' recommendation was, if the processing time of this new diarization model can be reduced, we would really appreciate it if you changed to the new diarization. It would improve data quality drastically. That would be very nice. The last point on my slides is a small outlook. As I said before, in the future we want to expand our test data sets, build bigger data sets, so we can have like that the numbers will be on a good basis and better basis. And we are thinking, or we are just exploring the possibilities of building something like an evaluation platform. It's a thing of the future, and we don't know how this will develop, but it could be possible to not only evaluate one technology like speaker diarization. You could also integrate face recognition, evaluate face recognition, evaluate speech recognition with the word error rate, and so on. So this could be coming. We're not sure about this. Yeah, and some technical detail we need to research on the supervised speaker recognition, because there had been some problems with this metric. And so this has not only been done by me, of course. I used these, most of the time I used the PyNote metrics open source toolkit, and I integrated it. So I'm very thankful for Mr. Hervé Prédon, but I'm not sure if I pronounce it correctly, because he coded PyNote and PyNote metrics. And I'm also very happy to have used the open source software Grinote from Clément Page. And my thanks go out to them. And the third one is a messy documentation of my project, but I prefer if you come to me directly and talk about, because I have a master's in literature studies, and I'm not a programmer, but yeah, it's crazy times, so we do programming too. So yeah, thank you for the attention, and if there are any questions.
Thank you, Frank. That was a wonderful presentation, and it's very good to see that we're making new steps in stuff like this. So this is the next step in speaker recognition. So thank you for explaining this. And I was wondering if there are any questions in the audience about this. Yes, we have 2 questions at least.
Hello, I'm Chris here from Sportcast. Did you experience in the outcome of the results also, or how was your experience maybe with edge cases with audio recognition and speaker recognition? For example, if you have overvoicing, or you have 2 languages on the same track and these sort of things. So are they also included this testing at the end? Or?
That's a really good question, because we took I think, a more easy way out of this problem, because we have a very restricted data set. And you have to start with a very restricted data set to start off, but I know that the PyNote metrics has it's possible to use the overvoice problem to engage the overvoice problem. It's integrated there. So, but we just left this edge cases a little more of them out. You see, it's a small data set at the moment. It is a kind of a weak point at the moment, but it still says a lot about the results. Give a lot of information, because, and that's the other part of my answer, we don't sometimes, when the documentalist is able to decide, does this go to speaker diarization or not, then he will leave out critical, or like this edge case sometimes. So yeah, it's built for more special use case in this time.
Okay, thank you.
Yes, and there was another question from you, right?
Do you have an idea of what kind of size of data set you're targeting for the model to try and get enough good statistics to have a really good evaluation of?
Yeah, to get it more representative, or to me myself, I don't have. I think my colleague at the Bayerischer Rundfunk, who also helped me a lot, Mr. Konstantin Förster, he is more into statistics and data analysis, and he is guiding me, and I think it's something that I have to talk with him about. When do we reach a point where we can say this is really a representative result? But right now, yeah, no. That's my answer.
Thank you. We have time for one more question if there is one. Otherwise, we'll change. We'll thank Frank once again with an applause.